Welcome to today's explainer. Every photo filter you swipe on, every barcode scanner you use at the grocery checkout, even those face-blurring privacy apps, they all seem like completely different technologies, right? Well, actually, underneath that sleek, modern interface, they are all relying on the exact same handful of structured mathematical algorithms. So today, we're pulling back the curtain on those algorithms and showing you exactly what is happening inside your devices. To help us visualize these core concepts, I want to quickly introduce you to Techie, our little guide from AI Tech Hub. Okay, let's dive into this and uncover the 5 fundamental techniques that are doing the heavy lifting behind the scenes.
Section 1, what it actually is.
And this brilliantly illustrates our starting point. Because to you and me, a picture is a gorgeous sunset, or a smiling face, or a sweeping landscape. But to a computer, an image is literally nothing more than a massive grid of numbers. That's the whole shebang. Every single dot of light, which we call a pixel, is represented purely by a numerical value. So processing an image means you aren't manipulating light or paint, you are just doing math on a giant spreadsheet. There's a simple rule for how complex this grid actually gets, and Techie is here to help break it down. For a black and white or grayscale image, you just need one single number per pixel to tell a computer exactly how bright or dark that specific dot should be. But for a full color image, you need 3 numbers per pixel, usually representing your red, green, and blue values. This simple distinction sets the foundational rule for everything we're about to discuss without needing to get bogged down in any crazy math.
Section 2, the main algorithms. Our first technique, and the absolute king of image processing, is convolution. Think of convolution as the fundamental mechanism. You take a tiny, separate grid of numbers, a sliding kernel, and you slide it, step by step, across the massive grid of your main image. As it slides, it multiplies and sums the values underneath it to transform the original numbers. It's kind of like passing a mathematical magnifying glass over the picture, altering it inch by inch. And this is the foundation that nearly everything else builds on.
So the crucial point is, how do we apply that sliding grid to solve real-world problems? Well, the first common problem we face is roughness, or visual noise. We've all seen this. Sometimes an image is just too sharp, grainy, or rough to be useful for a computer or even pleasing to the human eye.
The solution to that roughness is our first actual pillar, the Gaussian blur. By using that sliding convolution technique we just talked about, Gaussian blur mathematically averages out the pixels. It blends those harsh, rigid numbers in the grid with their neighbors. It gently softens the entire image perfectly so that the overall picture becomes incredibly smooth and cohesive.
But what happens when you need the exact opposite of smooth? That brings us to our second big challenge, needing to know exactly where an object begins and ends. If your phone is trying to scan a barcode, or if an app is trying to lock onto your face to apply a fun filter, it absolutely has to find those boundaries precisely. Our second pillar, edge detection, is the perfect solution for this. Edge detection strips away all the smooth, flat areas of an image and hunts specifically for sharp, sudden changes in the numbers. It isolates the exact points where objects actually end. It basically reduces a busy, noisy photograph to its pure structural outlines. And that's what allows a computer to instantly recognize the shape of a barcode or the silhouette of a person.
Let's move to and see how this builds into another really common challenge: separating crucial elements from background noise. Sometimes you don't just want outlines, right? You want to isolate an entire object and completely ignore everything else around it. You need the computer to make a definitive, hard choice.
That definitive choice is made by our third pillar, thresholding. Thresholding is a highly strict, uncompromising sorting mechanism. It basically splits the entire image into exactly 2 groups. It looks at a number and declares, okay, this pixel matters, and keeps it. Or, nope, this one doesn't, and totally deletes it. It's the ultimate tool for cutting a subject cleanly from its background. Now, we've all experienced this next problem firsthand. You take a photo, and the lighting is just entirely wrong. The image is way too dark, or it's totally blown out and bright, or maybe it's just completely flat and washed out. The visual information is actually sitting there in the grid, but the contrast is just terrible. Enter our fourth pillar, histogram equalization. This is the magical fix for bad contrast. What it does is analyze the spread of the dark and light numbers across the entire image grid, and then it stretches them out, mathematically rebalancing them. It takes a washed-out photo and redistributes the values perfectly, making sure the darks are truly dark, the lights are truly bright, and the details pop right out at you. Now, what's really interesting about this slide is that, stepping back to look at the big picture, we've explored 5 distinct techniques: the sliding grid of convolution,
the averaging of Gaussian blur, the outlining of edge detection, the strict sorting of thresholding, and the rebalancing of histogram equalization. While they achieve vastly different visual results, from blurring faces to scanning barcodes, they all share that exact same sliding grid foundation. They are all just brilliant ways of manipulating a simple grid of numbers.
To wrap up today's explainer, I want you to consider one final, really provocative question. Everything we just covered forms the absolute bedrock of classical digital image processing. But what happens when artificial intelligence steps into the ring? How are modern neural networks completely disrupting this numerical foundation we just learned about? If you want us to do a deep dive into that, drop the word pixels in the comments. Thanks for joining us to uncover the algorithms shaping our digital world and keep exploring the grids around you.